On October 4th, 2025, a photograph from Mars changed everything. The Perseverance rover captured an object in the Martian sky. It was not a small dot, not a blurry smudge, but an elongated glowing object, 4 times longer than it was wide, and immediately, the global online community erupted, and within just a few hours, 2 narratives emerged. On one side, Professor Lullaby from Harvard University explained it was just a simple camera trick, specifically, the stacking of images creating an illusion. On the other side, Dr. Horace True, a scientist who once worked at Caltech and Cambridge, refuted this, stating that the math did not add up. He argued that if this object were surrounded by a gaseous coma of green nickel, then its central part should also be green. But in reality, it was white. However, this is what was truly strange. NASA was silent, then the European Space Agency, ESA, followed by China, a nation that always releases images from Mars for propaganda purposes, and then the United Arab Emirates, the UAE, 4 rival space agencies competing on the international stage. All refused to release what their Mars orbiters had observed during the closest flyby in history. At the time it happened, the U.S. government shutdown affecting NASA began on October 1st, just 48 hours before the flyby event, a far too convenient coincidence. And now, as the interstellar object Atlas speeds towards the Sun, about to reach its perihelion on October 29th, we are faced with 2 possibilities. This is the most unusual meteor ever discovered, releasing industrial-grade nickel alloys and defying all our current natural explanations. Or 2, something far more extraordinary is happening in the Martian sky. In this video, we will analyze the evidence that both sides do not want you to see, the photographs, the silence, the anomalies, and the reason why October 29th could be the day everything changes. If you are as fascinated by this event as I am, please press the like button and subscribe to stay updated. And also let me know in the comments where you are watching from, what time it is there, and which explanation you find more convincing, a camera artifact or something else entirely. And if you want to help our community grow, please share this video on X or Facebook, Reddit, or your messaging app. Thank you for always supporting us. Chapter 1. The Pictures That Changed Everything. Let's begin at the starting point, or at least what most of us perceive as the starting point. October 4th, 2025. A day that would either go down in history as a turning point in human understanding, or just another moment where we got carried away by wild speculation. The verdict is still out, and that is precisely what makes this story so compelling. The Perseverance rover was parked in the Jezero crater on Mars, having been given an unusual task for days. Engineers back on Earth had been preparing for this moment. The third confirmed interstellar object ever detected, named 3IATLAS, was making its closest approach to Mars at a distance of 38 million kilometers. But in cosmic terms, this was practically a handshake. This was humanity's best chance to get a clear look at an object from outside our solar system, from the vast, dark void between the stars, a place where we had never sent a probe, never taken a picture, never truly understood what might exist out there. The rover's right-hand navigation camera, or NavCam, began its imaging sequence. These are not the high-end color cameras that give us those beautiful panoramic shots of the Martian surface. Rather, the NavCam is more utilitarian, designed to help the rover navigate, avoid obstacles, and plan its route across the rusty terrain. It takes black and white images with an angular resolution of 33 milliradians per pixel. These specifications might seem meaningless until you understand what they translate to. At a distance of 38 million kilometers, that's about 12,500 kilometers per pixel. Think about that for a moment. Each pixel in the image represents an area larger than the diameter of the Earth. You wouldn't be seeing fine details, not counting windows on a starship or reading a serial number, but you should be able to make out the object's rough shape, especially if multiple images were combined to reduce noise and enhance the signal. And that's exactly what happened. The Perseverance team, or perhaps more accurately, the amateur astronomers who monitor the raw image feed, began stacking the navcam frames on top of each other, and not just 2 or 3 images, where hundreds of images were taken over a period of about 10 minutes on Mars. Image stacking is a common technique in astrophotography, used when you are trying to capture a faint object. You combine multiple exposures, and the random noise is canceled out, while the actual signal is added together. This is how amateur astronomers capture nebulae with backyard telescopes, and how professionals tease out the faintest galaxies at the edge of the observable universe. When those images were stacked, an object appeared, not as a circular dot, not a fuzzy blob with a tail behind it like every comet we have ever seen from Earth, but a streak of light, an elongated feature about 4 times as long as it was wide, glowing prominently against the background stars, and, most importantly, it appeared white in the center with a greenish tinge around the edges. The image went viral on social media within hours, and threads on Reddit exploded with hundreds of comments. The social network X, formerly Twitter, lit up with amateur astronomers, conspiracy theorists, professional scientists, and everyone in between weighing in. YouTube channels rushed to analyze the pixels, enhancing the contrast to draw their own conclusions. And at the heart of it all was a seemingly simple question that carried immense weight. What were we actually looking at? The mainstream explanation arrived quickly. Avi Loeb, a professor of astrophysics at Harvard and the director of the Galileo Project, had been tracking 3IATLAS since its discovery in July. He had published papers suggesting that the object exhibited anomalous properties, anomalies that didn't quite fit the profile of a typical comet. But as the Perseverance image went viral, with people questioning whether it showed a cylindrical spacecraft, Loeb took to his blog to explain what he believed was happening. The elongation, he wrote, was an artifact, not of alien technology, but of simple physics and the way cameras work when objects are in motion. 3IATLAS was moving at about 67 kilometers per second relative to the Sun, in a retrograde orbit, meaning opposite to the direction of Mars's travel. From Mars's perspective, this object was streaking across the sky. Within 10 minutes, it would travel about 50,000 kilometers. If you were to stack the hundreds of individual frames captured during that time, you are essentially creating a time lapse, where the object's motion becomes blurred across the image. This ultimately creates the illusion of a long object, much like taking a photograph of a car passing by at night. With a long exposure time, the car itself may be compact, but in the photograph, it appears as a streak of light stretching across the frame. The headlights and taillights leave a blurred trail. You would not conclude the car is shaped like a ribbon just because the photograph shows it that way. Loeb had carefully calculated the angular resolution of the navcam, which meant each pixel covered 12,500 kilometers. At the distance of the Atlas object, the streak appeared to be about 50,000 kilometers long. Divide that figure by the object's velocity relative to Mars, about 91 kilometers per second, taking into account the motion of both, and you get about 9 to 10 minutes. This number matches the integration time necessary to stack enough frames to bring the faint object above the noise threshold. The math checked out. The explanation was elegant and straightforward. It was based on well-understood principles of imaging and motion. Case closed, right? Not in everyone's opinion. Dr. Horace Drew, who uses the online alias Red Collie, was not someone to be easily dismissed. His credentials included work at Caltech and the MRC Laboratory of Molecular Biology in Cambridge. He had published research on crop circle DNA and what he described as extraterrestrial computer code. To some, he was a maverick, willing to explore ideas that the mainstream dismissed. To others, he had ventured too far into speculation, but his counter-argument to Loeb's explanation gained traction because it focused on something observable, something within the images themselves. Drew pointed out that enhanced color versions of the stacked images showed something crucial. The center of the streak appeared white, while the edges showed a faint green hue. This, he argued, was consistent with observations of Comet Atlas from Earth-based telescopes, showing a green, nickel-rich coma, a cloud of gas surrounding the nucleus. If the complete elongation were purely an artifact from stacking images of a small, rocky sphere, moving through a larger green gas cloud, then stacking the frames horizontally would result in the center appearing predominantly green. So much green would accumulate from the coma in each frame that the final stacked image could not maintain a bright white center. Unless, Drill suggests the object itself is white, extending in an axial structure as he described, and is significantly larger than the green coma surrounding it, in which case, stacking the images would preserve the white dominance at the center, because there is simply more white material than green in each individual frame. It's a geometric argument about ratios and how colors combine when you stack images, and it is not easily refuted without a detailed model of the coma's extent and brightness at that distance, how it would appear in the black and white navcam photos, which were later colorized, and what the actual size and shape of the nucleus might be. Drew also emphasized that many Mars orbiters from different nations had taken images during the flyby. The Mars Reconnaissance Orbiter, the Mars Express, the ExoMars Trace Gas Orbiter, China's Tianwen-1, the UAE's Hope probe. All of them pointed their instruments at 3IATLAS during its closest approach on October 3rd. However, as of October 6th, when Drill and others were posting their analyses, not one official processed image from any space agency had been released. The Perseverance nav-cam frames were publicly available because NASA posts them automatically, but the high-resolution images from the HiRISE camera on the Mars Reconnaissance Orbiter, capable of 30 kilometers per pixel resolution, at the distance of BAI-Atlas, had still not been released. Spectral data that could reveal the coma's chemical composition, color images from CASES on ExoMars, infrared observations from HOPE, all remained behind closed doors. Why the silence? NASA's answer was straightforward. The United States government had entered a shutdown on October 1st, 2 days before the flyby event, and thousands of NASA employees had been furloughed. Websites were not being updated. Press releases were not being drafted. The agency, in its own words, was operating with a skeleton crew, focusing only on mission-critical activities. The processing and release of images of an interstellar comet, no matter how scientifically interesting, clearly did not qualify as a mission-critical activity during a budget shortfall. But the timing made many suspicious. The shutdown began exactly 48 hours before the most anticipated astronomical event in years. It felt almost too convenient. And it also didn't explain why the ESA, the European Space Agency, which operates independently of American budget politics, was also silent, or why China, a nation that regularly released images from its Mars missions as a matter of national pride, and to showcase the capabilities of their space program, had not shared anything, or why the UAE, eager to demonstrate the success of its HOPE mission, the first Arab interplanetary probe, hadn't seized the opportunity to show the world what its instruments had captured. This wasn't just one agency stalling. This was a coordinated silence among geopolitical rivals, nations that competed for prestige, funding, and influence in space exploration. And that silence, more than any single photograph, had become the story. Because in the absence of official data, speculation had rushed in to fill the void, and with Comet Atlas, there was plenty to speculate about. Chapter 2. 2 options, 1 truth, The debate crystallized into something like a scientific showdown, playing out not in peer-reviewed journals with their months-long review process, but in real time on blogs, social media platforms, and hastily arranged video conferences. This was not how astronomy usually worked. Typically, observations were made. Data was carefully analyzed. Papers were written, submitted, revised, and eventually published. The process required time, patience. Peer review ensured that errors were caught, that alternative explanations were considered, that conclusions were supported by evidence. But Comet Atlas allowed no such luxury. It was on the move, each day carrying it millions of kilometers closer to the Sun, approaching its perihelion on the 29th of October. After that, it would swing around and begin its journey back out of the solar system, speeding up as it escaped the Sun's gravitational well, ultimately set to depart our celestial neighborhood. Forever, the window to observe it, to gather data, to understand its true nature, that window was closing. And so, the debate unfolded at a rapid pace among scientists, amateur astronomers, and interested observers, all weighing in simultaneously. The core question seemed simple. Was the elongated appearance in the Perseverance images a true physical feature of 3IATLAS? Or was it an optical illusion created by the way the images were captured and processed? To understand why this was important, you need to grasp the implications of each answer. If it was a camera artifact, then 3IATLAS was likely a relatively compact object, perhaps only a few kilometers across, surrounded by a faint coma of gas and dust. Certainly unusual due to its interstellar origin and its chemical composition, but still fundamentally a chemically peculiar comet. Yes, a strange orbit. Absolutely, but a natural object nonetheless, formed in another star system billions of years ago, ejected by gravitational interactions, and now happening to pass through our solar system. If it was not an imaging artifact, if the object truly possessed an elongated structure, then the discussion changed dramatically. Natural objects in space tend to take on certain shapes. Small bodies are irregular, like asteroids, because their gravity isn't strong enough to pull them into a sphere. Larger bodies become spherical, or oblate spheroids if they rotate quickly. An elongation ratio of 4:1 is highly unusual for natural objects, not impossible, but it requires specific formation scenarios or structural compositions that could support such shapes against gravitational collapse or tidal forces. An elongated structure immediately invites comparison to Oumuamua, the first confirmed interstellar object detected in 2017. Oumuamua was also elongated, estimated at about 10:1, based on how its brightness varied as it tumbled through space. That elongation sparked endless debate, with some arguing it was a cigar-shaped asteroid, others suggesting it might be a flat disk seen edge-on, like a pancake. And Avi Loeb himself controversially proposed that it might be a light sail, a thin, artificial structure designed to be pushed by starlight. Oumuamua's elongation, combined with its non-gravitational acceleration as it left the solar system, an acceleration that couldn't be fully explained by outgassing like a normal comet, made it so unusual. The scientific community has largely settled on natural explanations, albeit strange ones, like the outgassing of invisible hydrogen or solid nitrogen ice sublimating in unusual ways. But the debate has never been fully resolved, and Loeb continues to argue that an artificial origin should not be dismissed. Without further evidence, 3IATLAS again potentially shows elongation, and if real, it would be the second elongated interstellar object out of only 3 ever detected. That is a pattern. 2 out of 3 is 67%, and if elongated shapes are rare, for natural objects, but common for interstellar visitors, you are forced to ask why. What makes interstellar objects different? Are we seeing selection effects, where only certain shapes survive ejection from their home systems, and the journey through interstellar space? Or are we looking at something else entirely? The mathematical arguments get complicated. Some astrophysicists not directly involved in the exchange between Loeb and True began to run their own simulations. If you model B-A-I-ATLAS as a point source, basically treating it like a star, and then track how that point would appear to move across the Martian sky, over 10 minutes, you can generate composite images, blurring each position to account for the navcam's resolution, stacking them and seeing the result. Those simulations generally supported the artifact explanation. A moving point source, when tracked and stacked, will create an elongated streak. The length of the streak matches the distance traveled during the exposure time. It is basic kinematics plus image processing. But the simulations made assumptions. They assumed B-A-I-ATLAS was point-like, that its brightness was concentrated in a small nucleus. What would happen if the coma expanded? What if it was already tens or hundreds of kilometers wide at that distance? Then, each frame would not capture a point, but an extended disk. Stacking extended disks over time produces a different result than stacking points. The streak becomes blurred, less defined, and the brightness distribution changes. And this is where things get interesting. The images show relatively sharp edges on the elongated feature. Not perfectly sharp, but sharper than you would expect if you were stacking images of a large, diffuse coma moving across the frame. That sharpness suggests that either the coma was smaller than expected, or the nucleus was brighter relative to the coma, or there was indeed something structurally elongated. Then there was the color analysis. Drew's point about the white center versus the greenish-blue edges was not easily dismissed. Other amateur astronomers began to offer their own ground-based observations. From early September, when Bi-Atlas was photographed during a total lunar eclipse, those images, taken with tracking telescopes that compensated for the object's motion, showed Bi-Atlas with what appeared to be an extended white core and a green halo. Then, an astrophotographer, Gerald Raymond, who had been imaging comets for decades, noted that this structure seemed atypical. Most comets show a bright nucleus with a gradually expanding coma that is more or less round or slightly elongated in the direction of the sun, due to radiation pressure pushing the dust away. Bi-Atlas in his photos looked different. The white region appeared elongated, even when properly tracked, and the greenish-blue coma seemed to form a distinct layer surrounding it, rather than a uniform glow. If you took those ground-based observations seriously, they suggested that the elongated white appearance was not purely an imaging artifact from Perseverance. It was visible from Earth, though more difficult to see due to the much greater distance and atmospheric blurring. Professional astronomers began to weigh in with caution. Some pointed out that determining the true shape of a comet from Earth or even from Mars' orbit is fraught with challenges. You don't see the solid nucleus directly. You are seeing sunlight, scattered by the dust and gas surrounding the nucleus. The distribution of that dust and gas depends on how the nucleus is outgassing, which in turn depends on its rotation, its surface composition, the angle of sunlight, and dozens of other factors. A spherical nucleus, with uneven outgassing from active regions, could produce an asymmetrical coma that appears elongated. But others noted that Atlas had proven itself unusual in many ways, beyond the shape debate. And this is where the conversation began to expand beyond just two options for a picture. The chemical composition kept coming up. Space-based observations from the James Webb Space Telescope in early August had revealed a surprise. Most comets are rich in water ice. As they approach the sun, water sublimates off the surface, creating their characteristic tails. But Atlas was different. Webb's spectrometer revealed that the coma was dominated by carbon dioxide, not water. 87% carbon dioxide by mass, 9% carbon monoxide, and only about 4% water. That ratio, 8 to 1 of carbon dioxide to water, was extreme. Solar system comets usually show the opposite ratio: more water than carbon dioxide. Some comets from the distant reaches of the solar system, from the Oort cloud, show higher carbon dioxide, but nothing like this. The only other interstellar comet, 2I Borisov, had shown a dominant water-rich chemistry, similar to solar system comets. Why was Atlas so dry? One explanation involves temperature. If it formed in a colder region of its home star system, farther from its star than our Earth-Sun distance, then its water ice might have been depleted early in its history, while carbon dioxide remained, or, if it had wandered through interstellar space for billions of years, cosmic rays could have altered its surface composition. But another chemical oddity adds to the mystery. Observations from the Very Large Telescope in Chile detected nickel atoms in the coma. Nickel itself is not shocking in a comet. Many comets show trace metals, but Atlas was producing nickel at an extraordinary rate. And most importantly, it was producing nickel without a corresponding amount of iron. In nature, nickel and iron are inseparable siblings. They form together in the cores of dying stars, and are blasted into space together in supernova explosions, and condensed into planets and asteroids together. Every rock we have ever analyzed from space, every meteorite, every asteroid sample shows nickel and iron in a nearly consistent ratio. They are chemically similar. They bond with similar materials. They do not separate naturally under normal conditions, except in industrial processes on Earth. We refine nickel from iron when we want pure nickel for specialized alloys, for anti-corrosion coatings, for high-temperature applications, nickel plating, nickel superalloys used in jet engines and spacecraft components. These technologies require separating nickel from iron through chemical or electrochemical processes. Data from the Very Large Telescope showed nickel emissions increasing significantly as Atlas approached the Sun. In just 1 month, from July to August, the production rate increased 25 times. That sharp increase followed a power law relationship with its distance from the Sun, suggesting that something about the surface was being heated and preferentially releasing nickel. Natural explanations did exist. Perhaps nickel-carbonyl compounds, strange molecules rarely seen in space, were sublimating off the surface, while iron compounds remained stable. That would be unprecedented, but not physically impossible. Or perhaps the surface composition was layered with nickel-rich minerals on top and iron-rich materials below, and only the surface was hot enough to release the metal. However, the alternative explanation, the one that caught attention and raised suspicion, was that the nickel signature matched what you would expect from technological material. If Atlas were artificial, if it had a metal hull or structural components, nickel alloys would make sense. They are durable, radiation-resistant, stable over a wide range of temperatures. Exactly what you would want for a probe designed for interstellar travel. But suggesting an object might be artificial, based on its chemical composition, is a leap. A massive leap. It requires extraordinary evidence, and so far, all observations can still be explained, however awkwardly, through natural processes. Strange natural processes. Yes, processes we have never seen before, but that is what makes interstellar objects so interesting. They are samples from other planetary systems, places we cannot visit, where conditions may have been very different from the formation of our own solar system. The debate over whether the extreme elongation was real or an imaging artifact refused to die down, because both sides had points that were not easily dismissed. And underneath it all was a growing realization. The images were only part of the story. The chemistry was only part of the story. Equally important was what we were not seeing. The data that should have been released but was not. The observations that multiple space agencies had made but refused to share. The silence seemed to grow louder with each passing day. Chapter 3. The Screaming Silence. The peculiar thing about silence is that it only becomes noticeable when you are expecting noise in an age of social media, instant updates, and space agencies competing for public attention. Silence from multiple organizations at once is a deafening scream. Consider the track record of China, the China National Space Administration, which has published over 14,000 images from its Martian orbiter Tianwen-1 since it entered orbit in 2021. And these are not just raw data dumps, but rather carefully processed, beautifully rendered images, released with press releases often timed to coincide with national celebrations, or to highlight China's growing capabilities in space. When Tianwen-1 captured a global color map of Mars at a resolution of 76 meters per pixel, the images were released within days. And when its accompanying rover, Zhurong, landed on the Martian surface and began transmitting pictures, China made sure the world saw them immediately. This is not unusual. Space agencies use their successes to justify their budgets, to inspire the next generation of scientists and engineers, and to demonstrate technological prowess. During the Cold War, the space race between the United States and the Soviet Union was as much about propaganda as it was about science. Every satellite launch, every crewed spaceflight, every moon landing was a statement. We can do this. We are advanced. We are powerful. That competition never really ended. It evolved. Today, China and the United States consider each other rivals in space. The Artemis Accords, an American-led framework for lunar exploration, has intentionally excluded China. In response, China has partnered with Russia to plan for an international lunar research station. The two powers barely coordinate with each other. The Wolf Amendment, passed by the U.S. Congress in 2011, explicitly prohibits NASA from bilateral cooperation with China without special approval. They do not share data. They do not collaborate. They compete, therefore. When 3IATLAS made its closest approach to Mars, and both NASA's Mars Reconnaissance Orbiter and China's Tianwen-1 were perfectly positioned to observe it, you would expect each agency to rush to publish their results. Imagine the headlines: China captures unprecedented images of interstellar visitor. NASA's HiRISE provides clearest view yet of mysterious comet. That is the kind of scientific achievement that resonates domestically and internationally, the kind of achievement that justifies funding and generates excitement. But neither published anything not processed images, not preliminary analysis, not even a brief statement confirming successful observations. NASA pointed to the government shutdown. This was real and had furloughed thousands of employees. But the shutdown did not prevent the Perseverance rover from continuing to automatically post raw navcam images. Those images are uploaded through systems that operate without human intervention, part of the mission's data management protocols. If raw navcam images could still be posted, why not raw high-rise images? Why would China, operating completely independently of American budget politics, also fail to publish anything from Tianwen-1? The United Arab Emirates added another layer of mystery, their HOPE orbiter. The Emirates Mars mission designed specifically to study the atmosphere of Mars across daily and seasonal cycles. It carries 3 instruments, including the Emirates Mars Infrared Spectrometer and the Emirates Mars Ultraviolet Spectrometer, perfect tools for analyzing the coma of a comet, to sweep for chemical signatures, to measure how the gases interact with solar radiation. And HOPE had a clear line of sight to Comet Atlas during the close approach on October 3rd. The UAE was incredibly proud of HOPE, as it was the Arab world's first interplanetary mission to Mars. In February 2021, the mission team regularly published data, released updates, and engaged with the public. The UAE Space Agency maintained an active social media presence, celebrating its achievements. They shared their science. However, after October 3rd, there was nothing. No images of Comet Atlas, no spectral data, no mention of the observations. aside from a brief pre-flyby statement confirming that they would observe. It was as if the event simply had not happened from their perspective. Despite months of anticipation, ESA, the European Space Agency, represented another puzzle. Their Mars Express and ExoMars Trace gas orbiter were both positioned to observe. ESA had announced in September that the observations would take place from the 1st to the 7th of October, specifying that Mars Express would use its high-resolution stereo camera and its spectrometer, while the Trace gas orbiter would use its color and stereo surface imaging system and its own suite of instruments. These were not casual observations. They were planned efforts, scheduled, coordinated, involving multiple teams across European nations. And then, silence. The ESA website showed no updates on the Comet Atlas observations. Beyond the initial announcement, no press releases, no preliminary findings, no images. For an agency that regularly shares spectacular images of Mars and frequently publishes results from its many missions, this absence felt deliberate. As observers began to point out this coordinated silence across geopolitical lines, some interesting historical parallels were drawn. There have been moments when rival nations have collaborated on matters of mutual interest. The Partial Nuclear Test Ban Treaty in 1963, signed by the United States, the Soviet Union and the United Kingdom, at the height of the Cold War, recognized that atmospheric nuclear testing threatened everyone, regardless of political ideology. Subsequent space rescue agreements and the Apollo-Soyuz test project, Soyuz in 1975, witnessed American and Soviet spacecraft docking in orbit, the crews shaking hands in space, while their nations remained ideologically opposed on Earth. Common themes, shared existential threats, when something threatens everyone equally, or when something affects the entire human species, confrontation becomes secondary to survival or understanding. The United Nations Office for Outer Space Affairs, in 1998, established guidelines, though not binding treaties, on how nations should handle the detection of extraterrestrial intelligence. These protocols emphasize that no single nation should make unilateral announcements, and confirmation must be verified. The international community should be informed, as premature disclosure could cause panic, misinformation, or international incidents if, and this is a significant assumption, the Mars orbiters had observed something that truly challenged the assumption that 3IATLAS was a natural object. You could construct a scenario where coordinated silence makes sense, not as a conspiracy, but as protocol, as caution, as an effort to verify findings before making irrevocable statements. But that requires believing that something extraordinary has been observed, and extraordinary claims, as the saying goes, require extraordinary evidence. Silence itself is not proof of anything, except that the images have not been released. There could be mundane explanations. Data processing takes time. Quality control requires careful review. Scientists want to publish findings in journals, not through press releases, to maintain credibility and priority of discovery. A government shutdown, even a partial one, disrupts workflows and delays publications. However, the pattern remained unsettling. 5 space agencies representing the United States, Europe, China, and the United Arab Emirates, all with active Mars missions, all positioned to observe the same event, and all chose not to share their results immediately afterward. 5 agencies that don't usually coordinate, competing for prestige and budgets, were suddenly united in their silence. Online communities began to track this obsessively. Reddit threads on r/space and Ars Astronomy accumulated hundreds of comments, analyzing every angle. People noted that Tianwen, one, regularly posts images within 48 to 72 hours after collection. They pointed out that ESA had shared Mars Express images just days after they were taken. In previous instances, They highlighted that the UAE's HOPE mission has a public data portal designed for transparency. Someone noted that on October 1st, just 2 days before the flyby event, China's Tianwen-2 mission, a completely separate spacecraft on its way to collect a sample from an asteroid, had released a selfie showing Earth in the background. It was a beautifully composed piece of propaganda, showing the Chinese flag on the spacecraft with our planet as a backdrop, the timing of which felt significant to observers. China was perfectly capable of releasing space imagery in the exact time frame when the Atlas observations should have been processed. They chose to release a Tianwen-2 image, and they chose not to release the observations. From Tianwen, one of the interstellar visitor. Was that significant? Or just reading patterns into the noise? Seeing conspiracy where there was only random coincidence. The silence gave birth to theories, with some arguing that all the agencies saw nothing remarkable, that Atlas appeared exactly as expected, a comet, and thus there was no urgency to rush the results to the press, when papers could be properly written. But that didn't explain why China wouldn't capitalize on even mundane observations for a prestige boost. Others suggested a technical failure, that perhaps all the instruments malfunctioned simultaneously, but the odds of that seemed infinitesimal. More provocative theories suggested a deliberate suppression, that the high-resolution images had revealed geometric structures, something not easily explained as natural, that spectral data showed chemical signatures inconsistent with any known comet, that multiple agencies realized they were looking at something that required coordination to announce properly, if it was to be announced at all. One blogger compiled a timeline showing that in the 72 hours after the 3/10 flyby event, various government officials and scientists appeared on news programs discussing 3IATLAS. Avi Loeb was interviewed on Newsmax, sharing the screen with Congressman Timbershed, a member of the House Committee on Oversight and Accountability. In a separate news segment, Stephen Miller, Deputy Chief of Staff for Policy at the White House, was asked directly whether the president had been briefed on 3IATLAS. Miller's response was very diplomatic and vague, reassuring the public that the appropriate agencies were monitoring the situation, but offering no specific details about briefings or findings. The fact that White House officials were even being asked about a celestial object, that it had risen to the level of a presidential briefing, suggested this was being taken seriously at levels beyond mere scientific curiosity. The fact that a congressional representative was appearing on television to discuss it, that questions about 3IATLAS were being directed to White House staff, that the media was covering it as a developing story, not just as a scientific curiosity, all pointed to an event that had transcended typical astronomical observations. And yet, the core data remained locked away. The high-rise images, capable of resolving features 30 kilometers wide at 3IATLAS's distance during its closest approach, would show whether the brightness came from a large nucleus or something else. They would reveal the actual structure, if a structure existed. They would end or intensify the debates about interpretation, about shape, about the nature of this object. Those images exist. They were captured somewhere in NASA's databases, on servers that survived the shutdown. The highest resolution pictures of an interstellar object ever taken by human instruments were sitting there, either processed or awaiting processing, and no one was showing them to the world. The silence continued. The days passed, 6/10, 7/10. Speculation intensified in the vacuum, and as the world waited for official images that never came, another peculiarity of 3IATLAS began to attract attention, something that was visible in amateur observations, that had been taken before it disappeared behind the sun from Earth's perspective. Something had added another layer to an object that was already difficult to understand. It had changed color from red to green, and no one could explain why. Chapter 4. The green glow and the mystery of color in astronomy is informative. When an object in space appears red, blue, green, or any other color. It is telling you about its composition, its temperature, the processes happening on or around it. Sunlight is white, containing all visible wavelengths. When that white light shines on a comet, some wavelengths are absorbed by molecules in the coma and others are re-emitted through fluorescence. The color you see is the chemical signature of what is there. Green comets are not particularly rare. Many comets develop a green glow as they approach the sun, and the cause is well understood. A molecule called diatomic carbon, written as C2, forms when larger carbon-containing molecules in the coma are broken apart by the sun's ultraviolet light. This C2 molecule absorbs ultraviolet light and re-emits it at specific wavelengths in the green part of the spectrum, around 510 nanometers. It is a beautiful process, and it is so common that astronomers expect to see it in active comets containing carbonaceous material. Bialis was widely observed in July and early August, during which time it appeared red. The red color indicated that dust particles were reflecting sunlight with a slight bias toward longer wavelengths. This makes sense for a comet far from the sun, where sublimation is still minimal, and the coma consists mainly of dust particles gently released from the warming nucleus. Red meant normal, expected dust. Then came September 7th, 2025. A total lunar eclipse was visible from several locations on Earth, including Namibia. During a total lunar eclipse, the moon moves into the Earth's shadow, and the sky becomes darker than usual for a full moon night. This creates ideal conditions for observing faint objects without them being obscured by moonlight. It is a gift for astronomers. A few hours of darker skies without having to wait for a new moon. Two experienced astrophotographers, Michael Jager and Gerald Riemann, were in Namibia with their equipment pointed at 3IATLAS. Both had been photographing comets for decades. They knew what to expect, how comets typically behave, the colors they usually display. At various distances from the sun, their telescopes tracked biATLAS across the sky, compensating for the Earth's rotation and the comet's movement to keep it centered during long exposures. When they processed their images, something had changed. biATLAS was no longer red, it glowed green. A distinct emerald green color extended into a coma about 2.5 arc-minutes wide. The change was sudden and puzzling, from one color to another over a period of several weeks. G posted the images online with a caption noting the green coma. Turning to blue, he mentioned that a faint tail was also visible in the images from September 9th. The astronomical community immediately took notice. The color change from red to green meant that the comet's activity had increased, that gases were now dominating in the coma, not just dust. It suggested biATLAS was entering a more active phase, as solar heating intensified. But this is where things became strange. When scientists looked at the spectral data, a detailed analysis of the wavelengths being emitted, they could not find a significant amount of diatomic carbon. Several teams had obtained spectra of biATLAS in late August and early September, using professional telescopes. A paper was published by Luis Salazar Manzano, and colleagues at the University of Michigan specifically addressed this issue. They found an extremely low ratio of C2 to cyanogen CN, another gas. A ratio so low that they concluded that biATLAS was among the most carbon chain-depleted comets ever observed. Think about that. The comet appeared green, strongly suggesting the fluorescence of diatomic carbon. But spectral analysis showed that the molecule responsible for that green light was essentially absent. It was like seeing smoke without a fire, hearing a bell without the bell ringing. The effect was present, but the cause was missing. Several explanations were proposed. One related to the timing and location of the observations. Perhaps C2 was present, but in small quantities, and the green light was being produced efficiently enough to be visible even with depleted C2. Fluorescence efficiency can vary. A small amount of a highly efficient fluorescent substance could produce a noticeable light. Another possibility involves other molecules producing the green or green-blue light. Although C2 is the most common culprit, other molecules can fluoresce at similar wavelengths. The trick is finding out which ones, because you need molecules that can survive in the cometary environment and react to solar ultraviolet radiation in just the right way. This is where cyanide enters the story, not the poison you find in detective novels, although it is chemically related. Cyanogen, or CN, is a free radical formed from carbon and nitrogen. It is common in comets when CN absorbs ultraviolet light. It can emit light in the violet and blue parts of the visible spectrum. Analysis of the same data showed extremely high nickel production, noting that the production of cyanide from Comet Atlas was increasing sharply as it approached the Sun. The rate followed an increasing power law, with distance from the Sun to the power of 9.38. That is an extremely steep dependence, much steeper than for typical comets. Could cyanogen be responsible for the green appearance? Possibly. The CN emission bands extend into green-blue wavelengths under certain conditions. If CN is present in unusually high concentrations, and if dust scattering and other factors are contributing to the color perception, the combination could produce the observed green color without needing a large amount of C2. But this explanation requires Comet Atlas to have a very unusual chemical composition, not only depleted in carbon chains but also simultaneously rich in nitrogen molecules like CN. Why would an interstellar comet have this particular combination? What processes during its formation, or in its billions of years wandering through the galaxy, would create such a deviant composition? Native comets from our solar system show a range of compositions based on where they formed. Comets from the Oort cloud, the distant spherical shell of icy objects surrounding the solar system, tend to have different ratios of volatile substances compared to comets from the Kuiper belt, the flat disk of objects beyond Neptune. The differences relate to the temperatures during their formation and the amount of processing they have undergone from solar radiation. As to whether they had made previous close passes to the Sun. But Comet Atlas did not form in our solar system. It formed somewhere else, around another star, under conditions that we can only infer. Perhaps its home star system had a different elemental abundance. Stars form from clouds of gas that are not perfectly mixed. Some regions of the galaxy are richer in certain elements than others, based on the history of supernovae that enriched those areas. A star forming in a nitrogen-rich environment might produce comets with an unusual nitrogen-to-carbon ratio. Or perhaps Comet Atlas is old. Calculations based on its velocity and trajectory suggest it could be 7 to 14 billion years old, possibly twice the age of our Sun if it were that ancient. It would have formed in a period that astronomers call the cosmic noon. When star formation in the Milky Way was at its peak, conditions were different then. More supernovae, more radiation, a denser stellar environment. Perhaps comets from that era naturally have a different composition than those that form today. These are reasonable speculations. They are grounded in astrophysics, in our understanding of stellar evolution and galactic history. They allow Comet Atlas to remain a natural object, while still being extremely strange. But there is a competing thought that refuses to go away. If you were designing a probe to travel between the stars, what would you use for propulsion? Chemical rockets are inefficient for interstellar distances. You would need something more exotic, perhaps ion drives, expelling particles at extremely high velocities. Or, if you were clever, you might harness stellar energy as you pass near stars, sublimating volatile materials to generate thrust, using the star's own radiation to power your trajectory adjustments. If you wanted a probe to look like a comet to any observer, you might coat it in ices with volatile compounds that would sublimate predictably as it approached a star. Carbon dioxide ice would be a logical choice. It is stable at the very low temperatures common in space and sublimates vigorously when heated. If you need to generate thrust for small maneuvers, the controlled sublimation of CO2 from specific vents could accomplish that. And if your probe uses a coolant or nitrogen-based propellant, A leak or intentional release could produce cyanogen. When those materials interact with solar radiation, this is speculation, and it's important to emphasize that there is no direct evidence that Borisov is artificial. But the chemical peculiarities, the carbon chain depletion along with the cyanogen production, the appearance of the blue, 6 color without the expected molecules, all add up to a pattern that's difficult to fit with standard cometary models. An astronomer speaking anonymously to a science journalist noted that if you were to list all the observations of Borisov and ask how many could be easily explained by natural cometary processes, you would get a contradictory answer. Some things fit. Active comets outgas. They produce comas. They sometimes show unexpected chemistry. But when you look at the entire set of observations together, the combined probability of all these anomalies appearing in a single natural object starts to feel improbable. This is a Bayesian problem. Each individual oddity might be unlikely, but possible. The blue 6 color without much C2, well, rare. But maybe it's CN or something else. Nickel without iron is strange, but perhaps it's some exotic chemical process. The dominance of carbon dioxide. Unusual for the comets we're familiar with, but not impossible for an object from another star system. The elongated shape could be an artifact of the imaging, or it could be a legitimate, though uncommon, geometry. But multiply those probabilities together. If each anomaly has a 10% chance of occurring naturally, and you observe 7 independent anomalies, the combined probability is 0.1 to the power of 7, which is 1 in 10 million. However, the anomalies may not be entirely independent. Some could be related, sharing common causes, and the individual probabilities are largely guesswork. We don't have enough examples of interstellar objects to calculate real statistics, but the exercise illustrates why some scientists are beginning to feel that invoking natural explanations for everything about Borisov requires stretching credulity, not breaking it, but stretching it thin. The blue 6 light faded in the following weeks, as 3IATLAS moved closer to the Sun and eventually disappeared from Earth's view. Behind the Sun's glare in late September, ground-based observations were no longer possible. The object was too close to the Sun's position in the sky, lost in the overwhelming brightness. It would remain unobservable from Earth until early December, when it would emerge on the other side of the Sun, having completed its perihelion passage. This meant the Mars flyby on October 3rd was one of the last opportunities to study 3IATLAS before it reached its most active state, near perihelion. And with those observations still unpublished, as the silence from space agencies continued, the blue 6 mystery became another piece of a puzzle that refused to resolve into a coherent picture. What was 3IATLAS? A chemically strange natural comet with an unlikely set of properties, but possible, or something merely comet-like, while being something else entirely in nature? The answer, many believed, lay in the metallic signature, the continued strengthening of nickel production that defied easy explanation, and, perhaps most unsettlingly, the pattern of how that nickel was being released resembled something being activated rather than something passively sublimating. Chapter 5. Industrial Alloys from Deep Space. The Very Large Telescope, VLT in Chile, is not a single instrument, but an array of 4 enormous telescopes, each with an 8.2-meter primary mirror, which, when combined through interferometry, can achieve the resolution equivalent to a single telescope. Over 100 meters in diameter, it is one of the most powerful ground-based observatories in the world, operated by the European Southern Observatory, ESO, and it had been observing 3IATLAS since July. The UV's spectrograph, the ultraviolet and visual Echelle spectrograph, is particularly adept at detecting faint emission lines from metals. When atoms of elements like iron, nickel, sodium, or calcium are present in a comet's coma and are excited by the sun's ultraviolet radiation. They emit light at very specific wavelengths. These emission lines are like fingerprints, with each element producing a unique pattern, and the intensity of those lines tells you how much of that element is being released. Team 5, which monitored 3IATLAS with UVES, included Rohan Rahatki and his colleagues. They were specifically looking for metallic emissions, because previous observations of comets had shown the detection of metals is possible but challenging. The temperature in most comets is too low to vaporize the minerals containing these elements. You typically need temperatures above 1000 Kelvin to sublimate silicon or metal grains. Most comets, even active ones, do not reach that temperature until they are extremely close to the Sun. However, Comet Atlas produced metal emissions when it was still beyond 3 astronomical units from the Sun. That is 3 times the distance from the Earth to the Sun. And at that distance, solar heating is very weak. The intensity of sunlight decreases with the square of the distance. 3 times farther away means 9 times less solar energy per square meter. It should have been too cold for metals to sublimate, but there they were. The nickel emission lines clear and unmistakable, and as Comet Atlas moved closer to the Sun, those lines did not just gradually brighten. They surged from late July to late August, covering a change in distance from about 3.9 astronomical units down to 3.1 astronomical units. The nickel production rate increased 25 times, with much more nickel per second in just 1 month. The team modeled this increase and found it followed a power law. The production rate was proportional to the distance from the Sun to the power of negative 8.43 plus or minus 0.79. That is an extremely steep relationship. For comparison, most cometary emissions scale with distance to the power of negative 2 to negative 4. The sublimation of water usually follows an inverse square relationship with a power of negative 2, because it is driven by solar heating, which itself follows the inverse square law. An exponent of negative 8.4 means the production rate is extremely sensitive to distance. By getting just a little closer to the Sun, the emission rate jumps dramatically. That is not a gentle increase, it is explosive. And that pattern does not match the simple thermal sublimation of surface ice. Then there is the issue of iron, or rather, the issue of its absence. The same observations that detected the nickel emission also searched for iron emission lines. Iron should be there in every meteorite, in every asteroid, in every sample of cosmic material ever analyzed. Nickel and iron appear together. The ratio changes slightly depending on the specific mineral, but they are always present together. In the initial observations of Comet Atlas, iron was not detected at all. As the comet moved closer and the nickel signal grew stronger, iron finally appeared. But only when 3IATLAS was inside 2.64 astronomical units, and even then the ratio of nickel to iron was extremely high, much higher than in any solar system comet or the previous interstellar comet, 2I Borisov. The authors of the study described this as extremely puzzling. That's a bit of scientific understatement when researchers use phrases like extremely puzzling or unprecedented in a peer-reviewed paper. They are signaling that they have exhausted the usual explanations and are entering territory where new physics or chemistry might be required. So how is nickel separated from iron industrially here on Earth? We know exactly how to do this. The Mond process was developed in the 1890s, which uses carbon monoxide to form nickel carbonyl, a volatile compound that can be separated from iron ore. You heat the ore with carbon monoxide at a moderate temperature. The nickel reacts to form nickel carbonyl gas, which boils at 43 degrees Celsius. You collect the gas, then heat it to a higher temperature, where it decomposes back into pure nickel metal and the carbon monoxide is recycled. You are left with refined nickel. That is how we make the nickel, the high-purity kind for electronics, for corrosion-resistant alloys, for nickel plating. that protects steel components. It is industrial chemistry, perfected over more than a century, standard in metallurgy textbooks, and that is apparently happening on 3IATLAS, perhaps the natural alternative. Requires invoking the formation of nickel carbonyl through processes that we have never observed in a comet. If the comet contains icy minerals, nickel and carbon monoxide, which we know it has in abundance, then solar heating could potentially drive the reactions that form nickel carbonyl. That compound is volatile enough to sublimate at relatively low temperatures, much lower than the temperatures needed to vaporize metallic nickel or nickel silicates. The iron might remain bound in other minerals that do not form. Similarly, volatile compounds under the same conditions. Iron carbonyl does exist, but it requires different formation conditions. If the mineralogy of 3IATLAS is just right, with nickel preferentially available in forms that can react with CO, while the iron is locked away in more stable compounds, theoretically, you could get the observed separation, but that's a lot of ifs. It requires a very specific mineral composition. Unlike anything seen in solar system comets, it requires conditions that favor the formation of nickel carbonyl while suppressing iron carbonyl. And it requires these strange conditions to be common enough that a natural interstellar comet would exhibit them, although interstellar comets are extremely rare, and this is only the third one we have ever detected. The alternative possibility is that the nickel signature doesn't come from natural sublimation at all, but that it comes from a manufactured surface made of nickel, which is widely used in spacecraft construction. Nickel alloys are favored for components exposed to radiation, extreme temperatures and corrosive environments. Fuel tanks are often nickel-plated. We'll pass near Venus. Its orbit will bring it relatively close to Jupiter in March 2026. These are not collisions or even particularly close flybys by cosmic standards, but they are closer than you would expect statistically for a random orbit. Loeb calculated the probability that an interstellar object entering the solar system on a random trajectory would happen to pass close to multiple planets. The answer depends on how you define close, but using reasonable definitions of a close approach distance, the combined probability comes out to about 0.005 of 1%. 1 in 20,000. Again, not impossible. Improbable things happen. Lottery winners exist, although the odds are millions to 1. But you start to wonder when the improbabilities keep piling up. The timing is also important. The planets orbit at different speeds. Mars takes about 687 days to complete one orbit. Jupiter takes nearly 12 years. Venus takes 225 days. The probability that an interstellar object not only arrives on a trajectory that passes close to all three planets, but also arrives at the times when each planet happens to be in the right place in its orbit for a close approach. That probability multiplies the already low orbital probability by another factor. Loeb's rough estimate for the combined probability of both the orbital alignment and the timing works out to be about 1 in 200,000. You are stacking improbable events on top of each other. The seventh anomaly is perhaps the most speculative, but also the most intriguing. The direction of arrival for Atlas, when traced back into interstellar space, comes from a region of the sky near the constellation Sagittarius. Sagittarius. That in itself is not surprising. Sagittarius lies in the direction of the galactic center, a star-rich direction. But Loeb notes that this direction is within 9 degrees of another famous signal from that central region. On August 15, 1977, the Big Ear radio telescope in Ohio detected a strong, narrow-band radio signal lasting for 72 seconds. The signal was at the precise frequency where neutral hydrogen naturally emits, a frequency that many SETI researchers believe is a logical choice for interstellar communication, because any technological civilization would know about it. The signal was so unusual, seemingly artificial, So much so that astronomer Jerry Eman wrote "wow" next to it on the computer printout. It became known as the wow signal, and despite numerous attempts, it has never been detected again. Explanations range from terrestrial interference to a passing comet, somehow generating the signal at the right frequency, to yes, an extraterrestrial transmission. The mystery remains unsolved nearly 55 years later. So, does it mean anything that the trajectory of 3IATLAS, when traced back, is only 9 degrees away from the origin of the wow signal? Loeb calculates the probability of this alignment to be about 0.6%, remarkably good odds, better than some other coincidences, yet still not a certainty. But here's the question. If you were an extraterrestrial civilization, and you sent a probe to a solar system that you had detected, perhaps through radio transmissions from that system or through observing the transit of planets passing in front of their star, how would you announce your arrival? You might send a radio signal first, a message. "Hello, we see you." Then, if you wanted to send a physical probe, you might send it along the same trajectory, from the same location, so that anyone connecting the dots would recognize that the signal and the probe were related. It is speculation, and connecting 3IATLAS to the wow signal requires believing that both are artificial and related. That is a leap beyond what the data supports, but the alignment exists. It can be documented, and it adds another layer to a picture that is already strained by improbability. When you list them out, the scorecard of anomalies creates a cumulative weight, a large size for an interstellar object, a forward thrust, inconsistent with normal cometary behavior, an extreme chemical composition in nickel, with no iron, and a dominance of carbon dioxide, a blue 6 color without the molecules that should have caused it, a trajectory aligned with the ecliptic plane, an arrival time optimized for planetary flybys, and a heading aligned with a radio signal, a historical anomaly. Each anomaly has natural explanations. There may be strained explanations in some cases, explanations that require special circumstances or poorly understood chemistry, but they are nevertheless scientific explanations that work by finding natural causes for observations. Only when natural explanations become more contrived and improbable than artificial ones are you forced to seriously consider the latter, and that threshold is subjective. It depends on your prior beliefs about the likelihood of artificial explanations. If you think the probability of encountering extraterrestrial technology in our solar system is essentially zero, then no amount of anomalies will convince you. You will always favor even highly improbable natural explanations, because they are still more likely than aliens. But if you allow even a small prior probability that interstellar probes might exist and could occasionally pass through our solar system, then each anomaly updates that probability upward, and with multiple anomalies combined, what began as a very small probability becomes less small, still unlikely, perhaps, but not dismissible. Loeb has been clear about this. He has said many times that 3IATLAS was most likely a natural comet, but he argues, and this is where the controversy lies, that the possibility of it being artificial should be seriously investigated, that we should gather as much data as possible, that we should use our best instruments, point our radio telescopes at it, analyze every spectrum, and track any deviation from purely gravitational motion, because if there is even a 1% chance, even a 0.1% chance, that we are witnessing a probe from another civilization, the implications are so profound that we have a responsibility to check thoroughly. The cost of being wrong is small. We observe an unusual comet and learn something about interstellar chemistry. The cost of ignoring it, if it is artificial, is that we miss first contact. This reasoning divides the scientific community. Some see it as proper diligence and open-minded inquiry. Others see it as sensationalism, as lowering the standard of evidence in pursuit of unlikely scenarios. The debate reflects deeper questions about how science should handle truly anomalous observations. how we balance skepticism with curiosity, how we decide when something is strange enough to warrant special attention. And all 7 anomalies and the arguments about their significance would reach a critical moment on the 29th of October, as Atlas passed its perihelion and faced the full force of solar radiation at its closest approach to the Sun. Chapter 7. What the Politicians Knew. There is a particular ritual in Washington when scientific matters intersect with national security. Information flows through channels the public never sees. Intelligence briefings happen behind closed doors. Congressional committees with security clearance receive updates that are not included in press releases. And sometimes the carefully chosen words in public statements reveal that those in positions of power know more than they are saying. The questions began to surface on November 2nd, the day before Atlas reached its closest point to Mars. Stephen Miller, serving as the Deputy Chief of Staff for Policy at the White House, was making the rounds on the news shows discussing the government shutdown, routine appearances explaining budget negotiations, and the continuity of operations. But then on one program, a journalist asked a question that seemed to catch Miller slightly off guard. Has the president been briefed on Atlas? Miller's response was measured, calibrated. He confirmed that the appropriate agencies were monitoring the situation. He offered reassurances about scientific competence and thoroughness. He stressed that there was no danger to Earth, that the object would pass very far from our planet. But he didn't actually answer whether the president had been briefed. He didn't confirm or deny. He pivoted to talking about the capabilities of American space programs and the importance of continued investment in NASA. The non-answer was in itself informative. If Atlas were just an interesting astronomical object, a natural comet passing through, the expected response would have been simple. No, the president is not briefed on individual astronomical observations. Presidential briefings cover matters of national importance, security threats, diplomatic crises, not a comet, no matter how unusual. It does not often rise to that level. But Miller did not say that. He did not dismiss the question as absurd. Instead, he acknowledged it seriously. Speaking of oversight, using language that suggested continuous attention from federal agencies, that choice of words, the reluctance to simply say no, it suggested that 3IATLAS had indeed reached government levels, where decisions about information management were being made around that same time. Congressman Tim Burchett from Tennessee appeared on Newsmax. Burchett serves on the House Oversight and Accountability Committee, a committee with jurisdiction over federal agencies including NASA. He has been vocal about transparency, particularly concerning unidentified aerial phenomena, pushing for the declassification of government files, and the release of what agencies know about unexplained objects. The two men discussed 3IATLAS and its anomalies. This pairing was in itself significant. Congressional representatives do not typically share airtime with astrophysicists to discuss ongoing scientific observations. They do interviews about legislation, about policy, about political controversies. Science communication is usually left to scientists and educators. But here was a member of Congress, during a government shutdown, taking the time to publicly discuss an interstellar object. Burchett spoke of the need for transparency, of ensuring the public has access to information gathered by federally funded missions. He framed it as a matter of principle, that NASA's data belongs to the American people who paid for it, that there is no reason to withhold observations of a natural phenomenon. The implication was clear. Burchett believed something was being withheld, and he was using his platform to apply pressure, making it politically uncomfortable for agencies to remain silent. Then came Congresswoman Anna Paulina Luna from Florida. Luna had apparently been briefed on the images. Regarding the Perseverance rover, she had contacted Avi Loeb directly, requesting his analysis of the photograph showing the streak of light. This is unusual, as members of Congress receive regular scientific briefings, but they usually came from agency officials, from NASA scientists, from the designated experts of the Committee on Science and Technology. They don't usually call university professors for a second opinion. The fact that Luna sought outside expert analysis suggests that either she was not satisfied with the official explanations, or she received no official explanations at all. Both scenarios were concerning. If NASA provided briefings that did not adequately explain the images, that would imply that the agency itself was either uncertain or evasive. If NASA provided no briefings at all, despite congressional interest, it would suggest that information was being actively restricted. Luna went a step further. She sent a letter to NASA leadership advocating for the use of the Juno spacecraft, currently orbiting Jupiter, to study BAI-ATLAS, as the comet passed relatively close to Jupiter in March 2026. The letter emphasized the scientific value, the unique opportunity, and the importance of maximizing observations of interstellar objects due to their rarity. But letters from representatives to agency heads about specific science missions are not routine. Congress sets budgets and provides oversight, but they don't typically micromanage which specific astronomical targets a spacecraft should observe. That is left to mission scientists and peer review panels. Luna's letter suggested one of two things: special constituent interest, which seemed unlikely for an obscure astronomical event, or a special, informed concern that prompted her to personally intervene in mission planning. The pattern across these political interactions pointed to something: multiple members of Congress from different committees expressing interest in BAI-ATLAS, White House staff being questioned about presidential briefings, scientists being invited to share platforms with politicians. This doesn't happen for typical astronomical discoveries. No matter how exciting the science is, consider the comparison to when the first image of a black hole was released in 2019 by the Event Horizon Telescope collaboration. It was front-page news, a scientific triumph, the culmination of decades of theoretical work and years of data analysis. But no members of Congress went on television to discuss it. The White House did not issue a statement. It remained a science story covered by science journalists, celebrated by the astronomical community but not elevated to political discourse. Or take the example of the detection of phosphine in the atmosphere of Venus in 2020, which briefly suggested the possibility of microbial life in the Venusian clouds. It was a bigger story in some ways, touching on astrobiology and the search for extraterrestrial life. It generated excitement and debate, but again, there was no political engagement beyond the regular NASA press releases. BAI-ATLAS was different, and the difference seemed to be precisely the ambiguity, the unresolved questions, the potential for interpretations to shift based on what the data actually showed. There is a historical precedent worth considering. In 1960, when the first serious proposals for SETI, the search for extraterrestrial intelligence, emerged, scientists and policymakers quietly developed protocols for what would happen if an artificial signal were detected. Those protocols emphasized cautious verification and international coordination before any public announcement. The underlying assumption was that a unilateral disclosure by a single nation or organization could cause panic, could be misinterpreted, could trigger diplomatic incidents. Those protocols were not binding treaties. They were guidelines developed through workshops and conferences, recommendations for best practices. But they reflected a consensus that the detection of extraterrestrial intelligence is a species-level event with implications far beyond science, requiring coordination at the governmental level. If the observations of BAI-ATLAS produced data ambiguous enough to potentially suggest an artificial origin, even as one possibility among many, then it would be logical for federal agencies to brief elected officials, not to confirm alien technology but to inform them of an anomalous situation where public interest was high and where the data interpretation was uncertain, to prepare them for questions from constituents and the media, to coordinate messaging so that different agencies would not contradict one another. The shutdown complicated everything in the normal course of operations. NASA has public affairs officers, prepared statements, and coordinated communication strategies. But during the shutdown with the skeleton crew, that infrastructure was disrupted. The scientists left their jobs, unable to answer media requests. Press releases went undrafted, interagency coordination faltered, and into that void, individual scientists began to speak out independently. Group B posted daily blog entries. Other astronomers gave interviews to science journalists, and amateur researchers were analyzing on social media. Without central coordination, the story became fragmented. Multiple interpretations circulated simultaneously, with none officially confirmed. All were competing for attention from a political angle, which is problematic if you are trying to manage information about an ambiguous situation. The last thing you want is decentralized communication, where different experts offer conflicting interpretations. It makes management difficult. It makes maintaining a consistent message harder. It invites conspiracy theories because the absence of official clarity allows speculation to thrive. Some observers suggested this was intentional, that the shutdown was timed to prevent a coordinated disclosure, that by furloughing NASA staff, the administration created plausible deniability for why information was not being released. If the scientists were not working, if the data was not being processed, if the websites were not being updated, then of course there was silence. It was not suppression. It was logistics. But the timing could have simply been a coincidence. The government shutdown happened when budget negotiations failed, driven by political factors unrelated to astronomical events. And October 1st happened to be 2 days before the Mars flyby event, purely by chance. The federal fiscal year ends on September 30th, and continuing budget resolutions are either passed or fail based on congressional votes and presidential decisions to sign or veto. The trajectory of a comet does not influence that process. However, the coincidence gnawed at people in the same way that the 7 anomalies in 3IATLAS's orbit and chemistry accumulated into something that felt less and less like random chance. The timing of the political silence, of the technological silence from multiple nations, of a shutdown that disrupted communication precisely when it was most desired. All of it felt orchestrated, even if it was not. Dr. John Brandenburg added another voice to the political criticism. A plasma physicist, experienced in defense research, Brandenburg maintained a website called Blue Planet Red, where he discussed Mars research, including controversial theories about past nuclear events on Mars. He posted a video analyzing 3IATLAS, noting the White House statements and stressing that official reassurance often precedes more detailed revelations. Brandenburg's track record was mixed. He had published peer-reviewed papers on plasma physics, alongside speculative theories about ancient Martian civilizations that most scientists dismissed. He existed in that ambiguous space where legitimate credentials coexisted with fringe theories. But his involvement underscored how 3IATLAS had captured attention from such diverse quarters, from mainstream scientists to those operating on the fringes of accepted science. The political interest, the questions being asked at high levels, the unusual coordination needed to explain the silence among multiple nations, all suggested that it had become more than just an astronomical curiosity. It had become an event that required management, demanding decisions on what to say and when to say it, requiring briefings and coordination that went beyond typical scientific discovery. And that management, that careful control of information, could not last forever. Eventually, the observations would be processed, the papers would be published, the data would emerge into the public domain either through peer review or through leaks. The questions would demand answers, and those answers, when they came, would have to address not only what 3IATLAS was, but also why the response to it had required political involvement. Meanwhile, amateur astronomers did not wait for official channels. They had their own telescopes, their own processing software, their own communities to share and analyze data. And in the absence of professional releases, amateur observations became the main source of visual information about by Atlas. By Atlas, some of those observations raised new questions. Some seemed to show things that shouldn't have been there, and some were almost certainly artifacts, misinterpretations, or wishful thinking. But separating the signal from the noise when people are looking at faint objects through the atmosphere, with modest equipment, it becomes nearly impossible without professional resources to provide ground truth. Chapter 8. The amateur images NASA doesn't want you to see. Amateur astronomy has a rich history of contributing to professional science, discovering supernova, detecting comets, monitoring variable stars. All of these efforts rely in part on networks of amateur observers with backyard telescopes and a dedication to monitoring the night sky. There are thousands of amateur astronomers around the world, with equipment that just a generation ago would have been considered professional grade. CCD cameras, computerized mounts, sophisticated image processing software. The barrier between amateur and professional capabilities has blurred significantly. When by Atlas was discovered, amateur astronomers immediately began to track it. Coordinates were posted online. Ephemeris tables predicting where the object would appear each night were calculated and shared. Observation campaigns were organized through forums and social media groups. People wanted to see this interstellar visitor for themselves, to capture their own photons that had bounced off something from outside our solar system. One of those observers used the username Dobsonian Power, named after the Dobsonian telescope, a design popular among amateurs for its simplicity and large aperture. On the 3rd of October, as by Atlas made its closest approach to Mars, Dobsonian Power was observing from his location with a solar telescope, an instrument designed for observation, safely by blocking most of its light, while allowing specific wavelengths to pass through. Why use a solar telescope to observe a comet? Because Comet Atlas was in the sky, near the Sun from Earth's perspective, not directly in front of it, but close enough that daytime observation with specialized equipment became necessary. Solar telescopes with narrowband filters can detect bright objects near the Sun, which would be invisible to conventional telescopes obscured by sunlight. Dobsonian Power captured an image and posted it online. The image was heavily processed, enhanced to bring out faint features with the contrast pushed to its maximum. What emerged was controversial. A slightly elongated dark feature against a brighter background. It was grainy, indistinct, but undeniably showed some kind of structure. Within hours, the image went viral. The comment sections exploded with interpretations, some seeing clear evidence of an elongated object, vindication for the Perseverance images, while others saw nothing but noise, an artifact of over-processing the image, pareidolia, the human tendency to see patterns in random data. Some pointed out that solar telescopes are not designed to observe comets and that the optics could create distortion. Professional astronomers were quick to express their skepticism, the poor image quality, the over-processing without knowing the exact parameters of the equipment, exposure time, and processing steps made it impossible to assess what was real signal and what was an artifact. One astronomer noted that when you enhance an image too much, you can make anything appear structured. Noise patterns become features, and optical aberrations look like objects. The human brain does the rest, connecting the dots into shapes. But the technical limitations of the image did not stop it from spreading. News outlets picked it up, YouTube videos analyzed it, and comparisons were made to the Perseverance images, with earlier paired photographs, with artists' renderings of what an interstellar probe might look like, and, inevitably, images generated by artificial intelligence, AI, began to appear, purporting to show the true shape of Comet Atlas, sleek, metallic structures, with impossible detail, complete fabrications, but presented as enhanced versions or artists' interpretations. This wave of AI-generated content created a secondary problem. How do you distinguish genuine amateur observations, flawed but authentic attempts to image the object, from fictional renderings designed to generate clicks? Some of the AI images were obvious fakes, showing surface details that no telescope could resolve at those distances. But others were more subtle, showing plausible comet-like structures, with enough ambiguity to seem as though they could be real photographs. Meanwhile, legitimate amateur observations continued. Astrophotographers with tracking mounts, telescopes that automatically compensate for the Earth's rotation to keep the target centered during long exposures, were capturing better quality images. In an effort with a powered Dobsonian solar telescope, Jerry Raymond and Michael Jackson in Namibia captured a green hue. Other observers in the southern hemisphere, where Comet Atlas was better positioned before it swung behind the sun, uploaded their results to astronomy forums. These images showed something interesting when properly tracked and shot with narrowband filters, isolating specific emission lines. Comet Atlas appeared to have an extended white or yellow core, surrounded by a green halo. The core looked elongated in many of the better quality images, not dramatically so, but distinctly not round. The elongation was not 4:1, like the Perseverance composite image, but more like 2:1 or 1.5:1. Was this a real structure or still an artifact? Tracking telescopes compensate for the Earth's rotation, but the comet itself is moving against the background stars. If the exposure is long enough, that motion can smear the image, potentially creating an elongation in the direction of motion. But some were short exposures, under 1 minute, not long enough for significant smearing, and the elongation appeared consistently across different observers, with different equipment in different locations. An observer posting under the name Red Collie and identified as Dr. Horos Jew specifically spoke out about the color distribution, despite having posted enhanced versions of many amateur images, showing a white center and a blue periphery. His argument was that if the object were a small, spherical nucleus surrounded by a large, blue coma, and you were looking at it through a telescope that blurs the image slightly due to atmospheric turbulence and instrumental limitations, you would see a fuzzy patch that is predominantly blue. White should not dominate the center, unless the white-emitting region were larger than the blue-emitting region. Professional astronomers countered that comas are not uniformly bright. They are densest near the nucleus and fade with distance, and if you have a bright nucleus surrounded by a fainter coma, even if the coma is blue and extended, the central brightness from the nucleus will dominate the image, unless the exposure time is specifically calibrated to bring out the faint, extended emission. Most amateur images are optimized to capture the bright core, not the faint outer coma. Therefore, seeing a white center is not surprising. The back and forth between Drill and other observers highlighted a fundamental challenge. Interpreting astronomical images requires an understanding of the imaging process, equipment response, exposure settings, and the processing applied. Two people looking at the same raw data can produce different processed images, highlighting different features, and there are no agreed-upon standards for how processing should be done. Arguments about what the images truly show become subjective. Amateur images also suffer from signal-to-noise issues. 3IATLAS was never bright. At its peak, it reached about magnitude 8 or 9, too faint to be seen with the naked eye. But it is visible through binoculars or a small telescope under a dark sky. Most amateur equipment has limited sensitivity, and capturing a clear image requires long exposures, stacking multiple frames, and careful processing. Each step introduces opportunities for artifacts. Professional observatories have larger mirrors, better cameras, darker skies, decades of experience calibrating equipment. They know the quirks of their telescopes, how to correct for optical aberrations, how to flat field to remove uneven sensitivity across the sensor, how to subtract the sky glow. So amateur observers often lack that expertise or equipment. Their images are valuable for detection and rough characterization, but not for the detailed analysis of fine structural features. However, in the absence of professional images from the Mars orbiters, the amateur observations were all the public had, and that created a vacuum where speculation could thrive, unchecked in a way it would not have been if NASA or the ESA had released even preliminary high-rise images, even just the raw, uncalibrated frames. That would have anchored the conversation in reality. People could have debated what the professional images showed, but at least the debate would have been grounded in high-quality data. Instead, the conversation centered on amateur images, heavily processed and of varying quality, supplemented by AI-generated fakes, filtered through social media algorithms that prioritize engagement over accuracy. The loudest voices were not necessarily the most informed voices. The most sensational interpretations got the most shares, and the truth, whatever it was, became harder to extract from the noise. Some observers tried to inject some sobriety. They were giving tutorials on astrophotography, explaining common artifacts, demonstrating how processing choices affect the final image. They showed how easy it was to create false structures through over-sharpening, how cosmic rays hitting the camera sensor could look like stars or other anomalies, how diffraction spikes from the telescope's support vanes could be mistaken for real features. But nuance doesn't go viral. Careful explanations got fewer views than bold claims. And when people wanted to believe that something extraordinary was happening, they became selective about which expert opinions they trusted. Skeptical astronomers became part of the cover-up. Enthusiastic interpreters become truth-tellers. The normal quality control mechanisms of science, peer review and replication, don't work well on social media where anyone can post anything, and algorithms amplify whatever generates clicks. A website had emerged dedicated to collecting and analyzing all available images of Comet Atlas. The site was run by someone who called themselves an independent researcher who compiled amateur observations, professional press releases, scientific papers, and blog posts. But it also gave equal weight to unsupported speculation and carefully vetted data. A graph showing nickel emission rates from a very large telescope appeared alongside AI-generated images of hypothetical spacecraft. The mixture of credible and unreliable sources created an environment where distinguishing fact from fiction required expertise, which most visitors lacked. As October passed and Comet Atlas moved closer to the Sun, observations from Earth became impossible. The angular separation from the Sun dropped below the threshold where even specialized equipment could safely observe. By mid-October, the comet had disappeared into the Sun's glare from our perspective. It would remain invisible until early December when it emerged on the far side of the Sun. By then, perihelion would have passed, and the most intense activity would be over. That meant the amateur observation campaign was over just when things were getting most interesting. The last images taken before. Solar conjunction showed Comet Atlas brightening, its coma expanding, its green glow intensifying, all consistent with a comet approaching perihelion and outgassing more intensely as solar heating increased. Nothing in those final amateur images definitively settled the debates about its composition or structure. They showed a bright and fuzzy, active comet, moving across the sky as expected, but the absence of continuous observations from Earth meant that whatever happened at perihelion would be witnessed only by spacecraft. The SOHO Solar and Heliospheric Observatory, orbiting the Lagrange, one point between the Earth and the Sun. There are instruments that can observe the region near the Sun. The Parker Solar Probe, on its close flybys of the Sun, can capture glimpses. ESA's JUICE spacecraft is on its way to Jupiter, but with a favorable vantage point outside of Earth's orbit. It is planning observations for November. Those observations will be crucial, as they will capture by Atlas in its most active state, when solar energy is at its maximum, when outgassing will peak, when any unusual behavior would be most apparent if the object is about to do something unexpected. It is about to fragment or maneuver, or exhibit any characteristics that deviate from normal cometary physics. Perihelion is when that would happen. October 29th is the moment of truth. The day bi-Atlas will pass 1.36 astronomical units from the Sun, just inside the orbit of Mars, closer to our star than it has ever been in its billions of years of wandering through interstellar space. Closer than it was at its formation, around whatever star system it came from. Assuming that system's star is similar to or cooler than our Sun, what will happen? As gigawatts of solar energy pour onto its surface, will it survive intact? Or will the thermal stress fracture the nucleus into fragments? Will the outgassing increase predictably according to thermal models? Or will the steep power law relationships in nickel and cyanide production extrapolate to even more extreme rates? Will the object continue on its hyperbolic orbit, unchanged? Or will any non-gravitational forces from asymmetric outgassing measurably alter its path? And underlying all of those scientific questions is a deeper question that no one wants to say too loudly, but one that lingers in every discussion if bi-Atlas is artificial. If some of its anomalies point to technology rather than geology, is perihelion a scheduled event, a trigger point? A moment when solar energy charges systems that have been dormant for billions of years in the cold of interstellar space. Will something that looks like a comet under remote observation reveal itself to be something else when subjected to maximum solar input? This speculation is uncomfortable for scientists. It enters territory where data was thin and imagination filled the gaps. But October 29th had arrived, and when it did, someone, somewhere would be watching Chapter 9, October 29th, the moment of truth. Perihelion is not just a point on an orbit, it is a crucible for a comet. It represents maximum pressure, maximum energy input, maximum activity. The physics is very simple. Solar radiation follows the inverse square law at 1 astronomical unit from the Sun. At Earth's distance, the solar constant is about 1,360 watts per square meter, moving to 1.36 astronomical units, where bi-Atlas would reach its perihelion, and that number drops to about 730 watts per square meter. Still significant. Still enough to drive vigorous chemistry for an object that had spent billions of years in the cold of space, interstellar, where temperatures were only a few degrees above absolute zero, where sunlight was imperceptible. This represented a shock, even during its journey, through our solar system from beyond the orbit of Jupiter. Coming in, bi-Atlas had never experienced this intensity. And if the steep power law relationships governing its nickel and cyanide production held, if those relationships were extrapolated forward, then perihelion would trigger an outgassing eruption that would dwarf anything observed before. The SOHO Solar and Heliospheric Observatory has monitored the Sun continuously since 1995, positioned at Lagrange point L1, about 1.5 million kilometers toward the Sun from Earth. SOHO maintains a perpetual view of the solar disk and the space immediately around it. Its LASCO coronagraphs block the Sun's direct light, to observe the faint corona and to detect objects passing close to the Sun. SOHO has detected thousands of comets, most of them small, sun-grazing comets, which plunge near the solar surface and often disintegrate. The spacecraft was not designed to study interstellar objects, but its position and instrumentation made it capable of observing bi-Atlas as it passed through the inner solar system. The Parker Solar Probe presented another opportunity. This NASA mission, launched in 2018, was designed to fly closer to the Sun than any previous spacecraft, studying the corona and the solar wind from inside the orbit of Mercury. Its perihelion passes take it to within 6 million kilometers of the solar surface, close enough that the spacecraft needs a dedicated heat shield to survive temperatures exceeding 1,000 degrees Celsius. Parker would not be at perihelion at the same time as bi-Atlas. The spacecraft follows its own elliptical orbit, and the timing does not line up. But Parker's WHISPER instrument, the Wide Field Imager for Solar Probe, has a field of view that can capture objects in the inner solar system. Mission planners calculated that between late September and early November, WHISPER would be able to observe by ATLAS, at least peripherally, depending on its exact position and pointing schedule. The challenge with both SOHO and Parker observations is that they were designed for solar physics, not for detailed comet studies. SOHO's coronagraphs have a relatively coarse spatial resolution. They can detect the presence of a comet, measure its approximate brightness, and track its path, but they cannot resolve the structure at the level needed to distinguish a compact nucleus from an extended coma, let alone determine its shape or detect surface features. Parker's WHISPER has better resolution, but it is optimized for imaging the solar wind, not solid objects, and Parker's orbit means that any observations of BY-ATLAS would come from unfavorable angles, catching the comet in the background of solar observations. Rather than as a primary target, the spacecraft that could have provided the best perihelion observations was ESA's JUICE, the Jupiter Icy Moons Explorer. JUICE was launched in April 2023 and is on its way to Jupiter on an orbit that coincidentally places it in an excellent position to observe BY-ATLAS in November, about 2 weeks after perihelion. At that time, the comet would still be highly active, close enough to the Sun that outgassing would continue at a high rate, but far enough away that JUICE's instruments would not be overwhelmed by the Sun's glare. JUICE carries multiple cameras and spectrometers designed to study the icy moons. Those same instruments are perfectly suited for observing a comet. The Janus camera system can capture color images with good enough resolution to see structural details. The MAGIS spectrometer can analyze the chemical composition of the coma across visible and infrared wavelengths. The UVS ultraviolet spectrograph can detect gases emitting in the ultraviolet spectrum. ESA confirmed that JUICE would observe by ATLAS, beginning on November 2nd and continuing through the end of November. They emphasized that this would provide the best views of the comet in its most active state, when the tail would be fully developed and its brightness would peak. But the observations by JUICE would come after perihelion, whatever happened at the moment of closest approach, during the hours when solar heating reached its maximum, would occur when no spacecraft had an optimal view. SOHO might capture glimpses, and Parker might get distant images, but the detailed, high-resolution observations needed to definitively answer questions about its structure, about the nucleus's size and shape, and whether the outgassing was symmetrical or asymmetrical. Those observations would not exist for the very moment of perihelion. Earth-based astronomers were completely in the dark, as BAY-ATLAS remained on the far side of the Sun from Earth's perspective, obscured behind 147 million kilometers of glowing hot plasma. No telescope on Earth or in Earth's orbit could observe it. The geometry simply did not allow it. This observational gap was frustrating for scientists wanting to understand perihelion behavior, but it also created a peculiar situation for those who suspected BAY-ATLAS might be artificial. If something was about to happen, if a maneuver was planned, or if systems were about to activate, the moment of maximum solar energy input, while hidden from Earth's direct view, would be an optimal time. Some had noted this back in July, when the orbit was first calculated. Avilop had mentioned it in one of his papers, pointing out that BAY-ATLAS would be occulted by the Sun from Earth's view during its perihelion passage, if you wanted to perform operations without being observed by a particular planet. Arranging for perihelion to occur when that planet could not see you would be a clever move. Of course, this assumes that the orbit was designed, which remained entirely speculative. Natural orbits do not care about observational geometry from Earth. The fact that perihelion happened to occur when Earth could not observe it was simply chance, a consequence of when BAY-ATLAS entered the solar system and the trajectory it followed. Reading intent into it required believing that the entire journey had been planned. It was a leap unsupported by evidence, but the speculation persisted, and online forums discussed it widely. What if Comet Atlas used a solar Oberth maneuver? The Oberth effect is a real phenomenon in orbital mechanics. If you have a propulsion system and you activate it, while you are deep in a gravity well, moving at high velocity, you will get more change in kinetic energy than if you activated the same propulsion system in deep space. Performing a fuel burn at perihelion is the most efficient. If Comet Atlas wanted to change its orbit to switch from an escape trajectory, a hyperbolic one, to a bound orbit that would keep it in the solar system, the best place to perform that maneuver would be at perihelion. You would get the maximum efficiency from your propulsion system, whatever form it took, and if you timed it so that Earth could not directly observe the maneuver, you would have plausible deniability. By the time you came around the Sun and Earth could see you again in December, the maneuver would be complete, and you would be on a new orbit. But observers would need time to calculate your new trajectory and realize it had changed. This is science fiction territory. The actual evidence for a deliberate maneuver was absent, but the scenario was physically plausible, and that made it compelling for some. The natural expectation for perihelion was also dramatic. If Atlas was a comet, and if the steep power law relationships in nickel and cyanogen production continued, then perihelion would produce a major outburst. The production rate had increased 25-fold from late July to late August. Extrapolating that curve forward to perihelion suggested the production rate could increase by another 10 times or more. That level of outgassing could dramatically change the comet's appearance. The coma would expand, potentially growing to span hundreds of thousands of kilometers. The tail, which had been faint and short in earlier observations, would lengthen considerably, as solar wind and radiation pressure pushed dust and gas away from the nucleus. The brightness would increase, possibly making the comet visible to the naked eye. If it was not hidden behind the sun, thermal stress could also fragment many cometary nuclei, breaking them apart at perihelion as they heated up, causing the internal pressure to build up faster than it could be released through surface vents. If Atlas had a structural weakness, if its nucleus was a loose collection of smaller fragments weakly held together, the perihelion stress could tear it apart. Fragmentation events are spectacular. The nucleus breaks into 2 or more pieces, each developing its own coma. The brightening can be very sudden as new icy surfaces are exposed to sunlight. But fragmentation also marks the beginning of the end for a comet. With the fragments dispersing over subsequent orbits, their total surface area increases, and they sublimate faster than they would as a single body. Fragmentation is a death sentence for a comet, just slower than immediate disintegration. Would Atlas survive its perihelion intact? The answer would tell us something about its structure. A solid, coherent nucleus, whether of rock or ice, would survive, while a rubble pile might not. And if it were artificial, if it had an internal structure providing strength beyond what random aggregation would provide, that would be revealed in its survival. The wait was difficult. October 29th came and went. Atlas swept through perihelion while Earth remained blind, facing the wrong way, the sun itself blocking the view. Spacecraft gathered what data they could from their distant or oblique vantage points, somewhere in the inner solar system, hidden from our eyes. Something happened to an object that had traveled for billions of years to reach this moment. The solar heating vaporized the ice. Pressure built up inside the nucleus as gases expanded. Material streamed into space, driven by sublimation, by thermal expansion, by the relentless push of solar radiation. Nickel atoms, if the power laws held, were being released at an unprecedented rate, glowing green as they fluoresced under ultraviolet bombardment. Cyanide radicals formed and dissociated in complex chemical cascades. Dust particles lifted off the surface, carried along by the outgassing, catching the sunlight and reflecting it back into space, and then perihelion passed, and by Atlas began its outward journey. The distance from the sun began to increase, and the solar energy began to decrease. The intense activity of perihelion would gradually subside as the comet moved back into the cold of the outer solar system, but it would take time for the observations to reach Earth. SOHO data would be downloaded and processed. The Parker observations would be analyzed. The spacecraft couldn't transmit everything in real time. Data had to be stored, compressed, sent back to Earth via the radio telescopes of the Deep Space Network, received and decoded. Then the scientists would need time to interpret what they were seeing. Early November would bring the first perihelion observations. The JUICE spacecraft would get its views in the second week of November, and finally in early December. By Atlas would emerge from behind the sun. From Earth's perspective, ground-based telescopes could resume observing the comet's post-perihelion appearance, its brightness, its spectral characteristics, its trajectory. All of it would be carefully measured. If it looked like a normal comet after perihelion, active, but followed predictable models, that would be an answer. If it had fragmented, that would suggest an internal weakness, a natural structure that couldn't withstand the thermal stress. If it looked different, if its chemistry had changed, if its trajectory showed unexpected deviations, that would raise new questions. The wait until December felt endless, weeks of uncertainty, relying on incomplete data from spacecraft not designed for this task, watching internet speculation swirl, while concrete information remained scarce. Scientists tried to manage expectations. They reminded the public that data takes time to process, that preliminary results can be misleading, that good science requires patience. But patience is difficult when the stakes feel high, when an interstellar object could be the most important astronomical discovery of the century, or it could be nothing unusual at all, when the answer could redefine humanity's place in the cosmos, or it could simply add another data point to the catalog. Our comet, on October 29th, has come and gone. The moment of perihelion has passed into history, and Atlas, whatever it truly is, has continued its journey through space, carrying its secrets into the darkness beyond the sun, waiting to be seen again when Earth's orbit brings us back into alignment, waiting to reveal whether it survived, whether it changed, whether the moment of its closest approach and maximum solar exposure triggered anything unexpected, waiting to answer, if only partially, the questions that have accumulated over months of observation and debate. Chapter 10. What if we are wrong? There is a thought experiment that philosophers and scientists sometimes pose when discussing existential risk. Imagine you are given a sealed box and are told, there is a 10% chance it contains something that will end human civilization, but a 90% chance it is harmless. Do you open it? Most people say no. The asymmetry of the outcome makes caution rational. The 10% risk of catastrophe outweighs the 90% probability of nothing. Now, let's modify the experiment. The box is opening automatically in 1 month. You cannot stop it. You can study it from the outside, run tests, gather information that might help you prepare for what is inside. Do you look? Do you measure? Do you try to understand? Although understanding might be unsettling, that is roughly where humanity finds itself with Atlas, the object that is here, moving through our solar system, on a path we cannot change. Eventually, it will exit, continuing its journey through interstellar space. We can observe it or ignore it. We can gather data or remain willfully ignorant, but we cannot make it go away. The Trojan horse analogy that Avi Loeb invokes has historical weight. Around 1,200 years B. According to legend, the Greeks had besieged the city of Troy for 15 years without success. Then, they built a giant wooden horse, left it outside the city gates as an apparent offering, and sailed away. The Trojans, believing they had won, brought the horse inside that night. The Greek soldiers, hidden inside the horse, emerged and opened the gates for their returning army. Troy fell because they welcomed something they did not understand. If 3IATLAS is artificial, if an observed part of its characteristics truly indicates technology rather than geology, then its purpose is unknown. The default assumption, the optimistic scenario, is scientific curiosity. An advanced civilization sending probes to explore, to gather data, to learn about other star systems, just as we sent the Voyager and Pioneer probes out of our solar system. Peaceful exploration, with no hostile intent. But that assumption is just an assumption. We have no way to verify the intent. An object that appears to be a comet but is actually a probe could be gathering intelligence about our solar system, about Earth, about whether life exists here. It could be reporting back, transmitting data via methods that we cannot detect, or on timescales too slow for us to notice during its brief passage. Or it could be more directly concerning. The paper that Loeb co-authored with Adam Hibbert and Adam Crack is titled, "Is the Interstellar Object 3IATLAS Alien Technology?" Explored scenarios where the trajectory and timing are not coincidental, where the close approaches to Mars, Venus, and Jupiter serve purposes beyond random chance, where the perihelion behind the Sun allows for maneuvers or activities that Earth cannot observe. The paper carefully labeled itself as a pedagogical exercise, an exploration of possibilities rather than a statement of probability. But it outlined unsettling scenarios. If a civilization wanted to conduct reconnaissance of our solar system, the trajectory of 3IATLAS would be nearly optimal. Retrograde orbits are harder to intercept, and close passes of multiple planets allow for gravity assists to change trajectory, or for the deployment of smaller probes that could aerobrake into planetary atmospheres. The paper calculated that if 3IATLAS used a reverse solar overburst maneuver at perihelion, it could potentially change from an escape trajectory to a bound orbit, to remain in the solar system indefinitely. The optimal time for such a maneuver would be when Earth cannot observe it directly, which coincidentally is exactly when perihelion occurs. Is this what happened? There is no proof yet, as orbital calculations require precise position measurements over time, until Atlas emerges from solar conjunction in December and can be observed again. Astronomers cannot definitively determine whether its path has changed. And even if the orbit has changed, non-gravitational forces from asymmetrical outgassing could explain it. Comets regularly experience minor orbital changes from outgassing jets that create thrust. Distinguishing a natural orbital change from an artificial one requires detailed observations of where the outgassing occurs, its degree of symmetry, and whether the forces produced align with the observable jets. That level of analysis takes time and high-quality data, but this scenario raises uncomfortable questions. If an interstellar probe wanted to remain in our solar system, perhaps to continue observations for decades or centuries, how would we stop it? The answer is, we could not. Our fastest spacecraft travel at speeds of a few tens of kilometers per second. Atlas moves at over 60 kilometers per second relative to the Sun. We have no way to intercept something moving that fast. No propulsion system can match its velocity. No weapon can reach it. Even if we detected clear evidence of its artificial origin, even if we knew for certain that Atlas was technology from another civilization, our response options would be limited to observing and worrying. We could point more telescopes at it. We could attempt radio communication, although the round-trip light time to an object a few astronomical units away would make conversation impossible. We could alert international agencies, convene emergency sessions at the United Nations, and coordinate scientific responses. But in terms of practical defensive measures, we would have none. If the probe's intentions were hostile, if it was designed to assess our capabilities before some future action, we would be powerless to stop whatever might happen. Next, this is why some people argue against active observation.